This is a presentation on the topic groups by V. Hinduja, Assistant Professor, Department of Mathematics, St. Joseph's College for Women, Tirupur. Group, we can say a set of elements together with a single valued binary operation as a group if it satisfies four properties: closure, associative, identity element exists, inverse exists. Here we consider a set G of elements A, B, C, etc. together with a single valued binary operation circle plus. This is a general notation. Then G is a group if G is closed under the operation circle plus. That is, if we consider two elements A, B belongs to G, then the element A circle plus B should also belongs to G. Second one, the associative law holds. That is, if we consider three elements A, B, C belongs to G, then A circle plus B circle plus C should be equal to A circle plus B circle plus C. Third one, G must have a unique identity element, say E. If we consider addition as binary operation, then the identity element will be 0, and if it is multiplication, then the identity element will be 1. Fourth one, every element in G must have a unique inverse in G. Example of a group. First, we consider the set A is equal to 1 minus 1 I minus I. We can prove this is a group under multiplication. First, we will see the closure property. We consider two elements in A, minus 1 comma I. Then minus 1 dot I, which is equal to minus I. Since this element also belongs to the set A, the closure property is satisfied. We can verify this property for all the other pairs. Second one, associative. We consider three elements 1 minus 1 I belongs to A. Since both 1 into minus 1 into I and 1 into minus 1 into I are equal to minus I, and this minus I also belongs to A, we have the associative law satisfied. This condition is true for all elements in A. Since the single valued binary operation is a multiplication, the identity element will be 1. Since A has the identity element 1, the third property is also satisfied. Fourth property, every element in A must have a unique inverse. First, we consider the element 1 in A. Since 1 into 1 is equal to 1, the inverse of 1 in A is 1. Second, we consider minus 1. Since minus 1 into minus 1 is equal to 1, the inverse of minus 1 is minus 1. Next, we consider the element I. Since I square is equal to minus 1, we have I into minus I is equal to 1. So that the inverse of I is minus I, and that element also belongs to A. And obviously, the inverse of minus I is I, and also I belongs to A. Since all the elements in A have a unique inverse, fourth property is also satisfied. Therefore, the set A is equal to 1 minus 1 I minus I is a group under multiplication. Abelian group. If a group G satisfies the commutative property, that is, for every pair of elements A, B in G, if A circle plus B is equal to B circle plus A, then the group G is called an abelian group or commutative group. For example, the set of all integers 0, plus or minus 1, plus or minus 2, etc. is an abelian group under addition. Since A plus B is equal to B plus A is satisfied for every pair of integers. Finite and infinite group. If a group contains finite number of elements, then it is called a finite group. Otherwise, it is called an infinite group. The number of elements in a finite group is called the order of the group. For example, we consider the group 1, minus 1, I and minus I. Since this group contains 4 number of elements, this group is finite and is of order 4. And the second example is the set of all integers is an infinite group under addition. Finite and infinite order. We consider a group G and an element A belongs to G. The group G can be either finite or infinite. Then the element A is said to be of finite order if A satisfies the property A power S is equal to E, where E is the identity element for some positive integer S. If there is no positive integer S such that A power S is equal to E, then A is said to be of infinite order. If A is of finite order, the order of A is the smallest positive integer R such that A power R is equal to E. For example, we consider the group A is equal to 1 minus 1 I minus I, and we consider the element minus 1 in A. Since minus 1 squared is equal to 1, the element minus 1 is said to be of finite order. Since minus 1 satisfies the property A power S is equal to E. Here A is minus 1, S is equal to 2 and E is 1. Therefore, minus 1 is said to be of order 2. Similarly, the order of 1 is 1, I is 4 since I power 4 is equal to 1, and the order of minus I is also 4. Cyclic group. A group G is said to be cyclic if it contains an element A such that the parts of A, that is A power minus 3, A power minus 2, A power minus 1, A power 0, that is E, A square, etc. comprise the whole group. Then such an element A is said to be the generator, that is it generates the group. For example, we consider the same group 1 minus 1 I minus I. This group is a cyclic group since the parts of the element I comprise the whole group. That is, 1 is nothing but I power 4, minus 1 is nothing but I squared, I is nothing but I power 1 and minus I is I cube. Therefore, in this cyclic group, I is the generator. Thank you.